couple we've come back and actually put triangles back in.
Yeah.
Kind of come with the fibers. Done the best to put triangles in. Some of them, Dave's like, don't worry about it. So we're like, okay.
Yeah.
But some of the big critical ones we've come back backfield.
So is that how far you are through the layup there?
Yeah, we've done all these.
Okay.
We got these left to do.
Okay. All right. Excellent. So you're more than halfway through. So you're basically through the midplane, and then you're tapering back out to the outer plies.
Yeah,
So,
I think all the rest of these, you can see this is sheet 73. Well, there's another one back here somewhere because we've already put that ply on the other side of the midplane. So now we're pretty much duplicating this part of the layup, going back out.
Okay.
So it's nice because we took the notes. So you go back and you go, all right, 65A, 65. So there's my 65s that I already did. So you go and you go, okay, well, last time I did this one, I had to cut it there. So now I'll just go in and cut it there. I'll probably shift it down or up a little bit. It's not on the same place, but I already know what to do with it.
Right.
So then I cut it, start, and then we're recording start and end times to lay down each one. So we'll have the data for how long it takes. Some of them take a long time and some of them are quick, like this one's easy. So it's 15 minutes for me,
Right.
because I did it, so it's longer for me to do it. But then this one took a little bit longer. We also found as soon as you're up on these cylinders, it just goes. Because there's no change in curvature as you're going along.
It just wraps
And it
around.
just-
It's that fillet that
it's
is
the-
really time consuming.
The crossover. And this one's got two-way curvature, so you'll get some splitting down here as it tries to go around the bowl. And we had to cut this in two places, which is weird, but it's because you're going with this bowl shape here. So you've got three directions that are changing curvature around it. But when we sliced it, we did it parallel to the fibers, which is that. So we didn't really have to create any overlap joints there. We just did it in three pieces and then it went on.
Well, that one looks like it'd be a challenge.
That one's a little bit nasty. Although the top, I think it went on in one. Because the top part is cylinder. So all that goes down pretty easy. And if you're really thin crossing here,
Right.
then sometimes it'll behave itself. But we probably had some splitting in there. And a lot of times we live with the splitting. And it opens up a little triangle like that, and you can either put in a patch piece, a little thin piece to get some fibers there, or you say, I know I'm coming across with another one on this side that overlaps and covers that. So I'm not even going to bother with it because I got double coverage there anyway. When it follows the fillet, that's the worst.
So then you have to split it a lot.
Yeah, so then we had to make an overlap and do that in one piece. Then this piece had to be three slits to try and get that to work, and that got ugly.
So how much of this does fiber sim let you know, and how much do you can't figure it out till you get it out?
Well, I'll show you on the screen, but the plot for this one, I'm sure it showed red,
Oh yeah,
red,
Yeah.
and only down the center did it behave.
yeah.
And then this probably not much red on that, maybe a little bit of yellow. So,
Yeah.
so if you listen to the fiber sim, it kind of tells you where you're going to have problems.
That's where the splitting happened there.
Yeah, probably.
That's the set. Okay, so.
It's just because it's compounding curve.
And then what's the green? It's just that's the fiber
The
direction.
green is the center fiber, if you will.
Okay.
So you're supposed to start laying it up,
I got you.
tacking it down there, and then spreading it out as you go away from it. The green just tells you that's my fiber direction.
Yeah. Great.
hard to cut across?
Not at all.
Not at all.
As long as you're using a sharp razor.
So what's the thickness of the plies? I forget.
Maybe 2,000ths of an inch or
2,000.
3,000ths. It's not much.
So how long does it take for this stuff to cool off before you can work with it? Oh, I mean warm up.
We leave it out for about an hour, just to be safe. But it varies depending on how much is in the bag.
Yeah.
But it could be as short as like 45 minutes.
Yeah. What's the freezer keep it at?
the standard is to be at least at 0 degrees.
Uh-huh.
Ours tends to be around -4 degrees Fahrenheit, I believe.
With the fibers.
I'd like to graduate to Final Cut Pro, but I really need to do iMac Wins summer.
Is there cameras up on the ceiling on the track? Looks like last time I had this triangle off. They split this.
But for the most part, not bad.
Bagging for the autoclave took 5 hours. The first stage of bagging is to trim the edges of the laminate. Then tape is applied as an edge dam to prevent resin from flowing beyond the edge of the laminate. An outer perimeter of tape is laid for attaching the seal to the outer bag. Thermocouples are installed on the mold to track temperatures during the cure cycle. Peel plies are applied in several layers. They provide a non-stick barrier between the outer bag and the laminate. Peel plies also create a smooth outer surface for the laminate, important since the outer bag is typically folded and can bunch up. The perforated layer and breather strip enable air to be evacuated over the entire surface of the laminate. The non-perforated layer contains the flow of resin at cure temperature. The breather layer allows air to flow to vacuum ports in the outer bag. The outer bag is secured to the tape and vacuum ports are installed. After leak check, the part is ready for cure. The entire cure cycle took 7 hours. Visual inspection revealed good ply compaction and laydown. No ply bunching or wrinkling was observed. However, foam tool cracking at bond joints occurred sometime during curing or cool down. This indicates that more testing is needed for tool adhesives and sealants. Some areas of concavity had some bridging and resin pooling. This could potentially be addressed with local temperature expanding blocks, sometimes known as intensifiers, that provide extra pressure into the concavities. The engineering demonstration unit experience demonstrated the practicality of fabricating a complex contoured, thin-walled laminate structure of high-modulus fibers. Many valuable lessons were learned. For more information, see the NASA report documenting this effort.